But today, we're going to talk about the idea of programming to an interface, right? And this is is ultimately about the beginning of data structures, in the sense that we're going to start talking about abstract data types. And so programming to an interface in Java is essentially Java's way of supporting an idea called abstract data types. And starting next week, we'll get into abstract data types a little bit more in depth. But right now, we're just going to complete our understanding of how we define and use classes in Java. And then get to this idea of programming to interfaces, right? So last time, we basically talked about how to construct a class in Java in order to design a class, in order to be able to create new objects, right? So in general, we don't use static methods all that much in Java. And we don't use static fields all that much in Java. They have their use, but that's not exactly how it's supposed to work. The way it's supposed to work is you have a main program. OK, so that's static. You have a starting place for your program. But the program itself is creating and manipulating and otherwise interacting with objects. And those objects are defined by their class, right? And we saw that last time. And so we had this class triangle that we constructed. And a triangle was made up of information, right? The instance fields. And those fields defined a triangle. And so every triangle has its own values for those fields. And we can create new triangles, right? And similarly, we had instance methods, which were methods, functions, procedures, et cetera, that are defined in the context of a specific object, right? So now, instead of having a bunch of helper functions or a bunch of library functions that all say, OK, you give me the data that represents a triangle, and then I will give you an answer with respect to that data. Like, you give me the 6 numbers that represent a triangle, I'll tell you its category. You give me the 6 numbers that represent a triangle, I'll tell you its area. Instead, we now define a whole class called triangle and say 6 numbers are a triangle, define a constructor so that we can take any 6 numbers and turn them into a triangle, right? And then now just ask that triangle, what's your area? What's your perimeter? What's your category, et cetera? And those instance methods have access to the fields of the quote unquote this triangle, right? By the actual object that we used in order to get to that method, right? So that's the big difference between instance methods and static methods, or class methods, is that instance methods only make sense with respect to a specific object, whereas class methods are just available through the name of the class, right? So ultimately what it boils down to, like the idea here is that classes and objects are the fundamental units of abstraction in Java. And we can think of this in a physical analogy, kind of like a factory. The classes are a factory which can produce objects of that class, right? So when we write the triangle class, we're basically that code is a factory for creating new triangle objects. The instance fields, that's like the blueprint for a specific triangle. In order, a specific triangle has these values as its fields, as its value, as its state, in order to represent a specific triangle. And every triangle will have different, AX, BX, CX, CY, whatever. Like whatever fields a particular triangle has, every specific triangle has its own copy. Right? And the instance methods are the things that particular object can do. And so, right. Now, the static stuff, static fields, static methods, those are are part of the factory itself. So a static method is one that you don't need a specific triangle or a specific object in order to call that method. You can just call that method just using the name of the class. And so you might have auxiliary methods, helper methods, methods related to that abstraction that aren't necessarily, don't need to be executed in the context of a specific instance, but are related to that abstraction. And so that's why we put those static fields in that class, so that we bundle that together with all the other things that are related to that abstraction. Right? OK. And so let's see here. Yeah. So then the idea here is that we can think of also objects as state, right? When I have an object, behind that object in memory is the actual field values for the fields of that object. The actual values of those fields is the state of the object and defines the object. Right. So when we get around to when you're constructing a program and you're deciding what kinds of objects you need, what kinds of abstractions you want to represent and be able to manipulate, that's the art of object-oriented design, right? And so that sometimes is obvious, right? Oh, now in order to create a triangle, I want to make a triangle out of 3 points. In order to make a point, I need 2 numbers, an x and a y. And so sometimes it's pretty natural to know what fields I need to represent my abstraction. But sometimes it can be a little bit more difficult. Sometimes you have to make decisions as to what goes into an object and what doesn't, or what should be pulled out into a separate object, and the relationship between objects. And again, that's going to depend on the specific circumstances of the software that you're trying to write, as well as your experience as a programmer and the design of the system as a whole. But in general, an object, you don't just throw random information together and call it an object, right? That object design reflects a purpose, right? It reflects an idea, that abstraction. All right. Okay, so now that we have a better understanding of how classes are usually used, right? Classes are usually used to define a set of instance fields, a constructor, and a set of instance methods, so that now I have the ability to create new objects of that type and then use those methods in order to manipulate and work with those objects, right? So if that's how we usually write classes in Java in order to use them in our Java programs, what good are static class fields and static class methods? Well, like I said, sometimes you have information that you want to associate with a abstraction as a whole, right? And while it doesn't often come up, there are some use cases that come up more often than others. In particular, static class fields are often used to define named constants that are related to the abstraction. So for example, math.pi, right? The field pi inside the math class is the value of pi, 3.14, blah, 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 right? And that makes sense. I mean, it belongs in the math class because that's where all the other static math functions are defined. And it's a mathematical quantity that you may need in some of your programs. And it's a field because it's just, it's just a value. We don't need it to be there's no method to run. We just need to be able to get to that value. But it's a constant value. We don't ever want that value to ever change, right? Because we don't want to change the value of pi. So math.pi is defined as a static class field in the math class so that it's available for use just through the name math, right? Which is great. But in order to make it so that that field can never change, we need to make it a constant. We need to make it so that it can't ever change. And the way we do that is by using the final keyword, which we haven't really seen yet. But the idea of creating static final fields associated with the class in order to define named constants associated with that abstraction is generally the most common use of class fields. Otherwise, for the most part, we use instance fields to define the kinds of information that go into an object of that class, and we don't really use static fields for much else. All right, so we can going back to the last example of lecture 6, we can kind of complete our picture of point and triangle by making use of, right, so in the triangle, one of the things we said our original triangle definition was deficient in was that we were comparing the side lengths with double equals. And we know that we're not supposed to do that because those are real values. And we're supposed to define some sort of epsilon bound, which defines how close something needs to be for those two sides to be equal. And we're supposed to use, compare the two numbers, the difference of those two numbers with respect to that epsilon bound in order to decide whether two sides are the same. So the old code, the last version of our triangle looked like this, we had created a new abstraction called point, right? So we had this class point that put together an x and a y value into a point, and now we're able to rewrite our triangle so that we have a triangle defined as 3 points. That's great. But we're still in category using double equals in order to compare side distances from each other. That's not great. So we could make another improvement by essentially defining a epsilon bound. And again, because I'm going to want to use this and maybe in a number of different places, and I want to be able to refer to it by name, this is a perfect use for a static class field by defining a named constant. So it's static. That means it doesn't mean that means that the triangles don't have their own side epsilon. It's not like one triangle has one idea of how close two sides need to be equal, and a different triangle has a different idea, right? It's not that each triangle has its own value for this field. This field has a value for the idea of a triangle as a whole. The whole class has an understanding of how close two things need to be in order to consider the sides equal. So it's static in that there's only one value here. It's not a value per instance. It's a value for the whole class. It's final. That means that once I assign it, I'm never going to change it. And I call it side epsilon. So usually the convention here is when you have a named constant, you use all caps with words separated by underscore. That's the naming convention. I could have used any name here, as long as it was a legal name. But that's a general convention for when you're defining a name that is acting as a named constant in order so that if you see it somewhere, you kind of know that it's a named constant. So by defining this named constant, side epsilon, as whatever this value is, then I can create a little static helper function called sides are the same that takes in two numbers, s1 and s2, presumably side lengths, and then does the appropriate thing for deciding whether they are the same or not. And now I can use that sides are the same helper function in my instance method when I want to take two sides and compare them for being the same. The reason why sides are the same is static is because, let's see here, is because you'll notice nothing in this method, this little helper method, doesn't require any field values, right? I don't need to get to any of the points of a triangle. I'm not working with the fields of a specific triangle. All the information that is needed for this method is provided in the parameters. I'm giving it side 1, I'm giving it side 2, and I'm just getting back true or false. Are these two sides the same with respect to my epsilon bound? So if a method in a class doesn't actually need an instance in order to be useful, then there's no point in making it an instance method because you're not using any of the fields of any instance. You're just so you can define it as a static class method so that it is part of the class as a whole. I can certainly use the method inside an instance method, right? Here I'm taking my side AB and my side BC, and I'm sending them to that sides are same method, which that's defined in the same class. But I don't need a triangle, right? I mean, there's no reference. I don't need the sides are same doesn't refer to any of the fields that are part of the current triangle, and therefore there's no need for it to be an instance method. I can make it a static method. All right. Okay, so just kind of recapping now what we know. So now we kind of can see what's in a class, right? So any given class is going to have these kind of parts to it. It's going to have, if it's defining an abstraction, if it's modeling a particular kind of object, then it's going to define instance fields, right? That's the data that is specific to each instance of an object. It's the state of any given object, right? It might have static fields or class fields. Those are values that aren't associated with each individual instance, but are instead associated with the whole class as a whole. This is really annoying. I hate this thing. Right. And then, right, so that could be in it. We'll have a constructor, right? That's a special kind of method for initializing a new instance. We might have instance methods. Those are the procedures and functions that can be executed in the context of a particular instance, right? So I can ask a particular triangle, what's your area? What's your category? I can ask a particular string, what's your length, right? So I need a reference to an object, and then I say dot, and then the method name. And then the last thing that might be in a class is static methods. And these are often helper or auxiliary methods that are related to the abstraction, but that don't actually require an instance to use, right? So in our example, we had a little helper method called sides are same, which was used by the instance methods when they needed to compare two side lengths, but the method itself didn't need an instance in order to operate, right? It was given the two side lengths, and it just came back true or false because it compared it against that side epsilon. All right, so some classes might not have static fields. Some classes might not have any static methods, right? Generally, a class will almost always have instance fields because it's trying to define a new abstraction, right? And it generally, of course, it'll have a constructor to initialize a new object, and it'll have instance methods because you want to be able to work with that object. If we look at our triangle class, the way we ended up, right? We ended up with 3 instance fields, right? Every triangle has its own point A, point B, and point C. We ended up with a class field, this side epsilon named constant, which was a convenient place to define how close two sides needed to be, right? We had a constructor, of course, in order to initialize those points. I've actually kind of made a mistake here. The fields should have been declared as underscore A, underscore B, underscore C in order to match the field names I used in the constructor. But hopefully you can kind of see around that error. We had instance methods. These are methods that, in order to call, I need an instance because these methods are going to require the fields of a particular instance in order to come up with their answer, right? So if I'm going to ask for the category of a triangle, I need to ask for the category of a specific triangle. That's why category is a instance method, as is area and side AB, side BC, side CA, etc. Those methods are defined, are defined, or only make sense in the context of a particular object, right? And then we had one final class method, which was this little helper method for taking two side lengths and deciding with respect to that named constant side epsilon whether or not the two side lengths were the same. All right. Okay. So one thing that you might notice is that we still haven't used these access modifiers, public and private and protected. We're just declaring everything with no access modifier whatsoever. When you declare something with no access modifier, it means that any code in the same package can access these things however they want, right? But there's a danger to that, right? And so the access modifiers are actually really important for enforcing who can really work with and see what values and what methods. And that idea is this notion of encapsulation, right? So this is the last kind of object-oriented idea that we're gonna kind of talk about before we kind of jump into the data structure side of things. But encapsulation is this idea that you should try to hide information as tightly as possible. That you only want to expose things you don't want to expose things outside of the class that are really internal workings of the class that should only be manipulated inside the class itself. The idea being that if I write the triangle class, then I know what's going on. And so all my code that's in the triangle class should have access to everything, all the fields, all the methods, etc. Right? And so I know, since I'm the designer of that class, it's the onus is on me to do things correctly there. But it could be that that somebody is writing some program that is using my class, I want to limit their ability to change things that are part of an instance that they really shouldn't be messing with if they don't know what they're doing. And the tool that I have in order to decide what does code outside of my class get to see or access and what they don't get to see or access are these access modifiers. So here's an example that kind of motivates this idea. Let me get back to here, close everything. Right? So I've kind of simplified our classes a little bit. Here's our points, right? An x and a y value, a constructor that puts those two together, and a distance to method that allows one point to calculate the distance to another point. Fine. And here's our triangle, right? This is pretty much the same thing as before. I've cleaned it up a little bit by getting rid of a few things, renaming a few things. So instead of area and category, I just have perimeter as something that it can as an instance method, and I renamed the side length methods a little bit. And then I got rid of the sides are same and all that business because I didn't really need it here. But here's our triangle that takes in 3 points. You'll see that this parameter a, right, is a point that I pass to the constructor. The field happens to have the same name, and that's why when I set the field, I have to fully qualify the field name through the this pointer and say this.a equals a, because otherwise the compiler will understand a name to be the name. If the name is defined on the call frame, if there's a local variable or a parameter name with that name, that is what the name is going to be understood to be. And so, since I have parameter a and I have field a, I have to have a way of distinguishing which one I mean. So if I just say a and there's a parameter named a, then that's what you get. But if I meant a field named a, then I need to say this.a in order to be more explicit, in order to actually dereference the this reference, right, and say this dot, right? That means go to that part of memory, go to that object, look for a field named a, right? So this is, writing code constructors like this, where the parameter name is the same as the field name, and you say this dot, the field name equals the parameter name. That's kind of an old school way of doing things. That's kind of like my generation of programmers used to write our constructors this way. A more modern style, if you will, is to use some sort of stylistic convention with your field names that you don't use for local variable names and parameter names, so that if you see that stylistic convention in a name, you know that it must be a field name. And because you only use that stylistic convention with field names, it never conflicts with a local name, a local variable name, or a parameter name. And so then you never have to worry about having to say this dot in order to get to the field name. So the most popular of these stylistic conventions is to put an underscore in front of the field names, right? So now I have point underscore a, point underscore b, point underscore c. Underscore is a perfectly valid name character, and so I can start these names with underscore. Now, so a and underscore a, those are two different names, and so now I don't have to say this dot. I can just say underscore a equals a, and underscore b equals b, like this, right? Now, if I change it there, then I have to change it everywhere. Right. OK. So what was my point here? All right, so now here's my, here's my triangle, right? We're going through this example to motivate encapsulation. We see that we're not using any access modifiers. That means that any class in the package can access these fields through a reference, anytime it wants. In particular, I could write, so here's a different class in the same package. It's a little little example program. So it's a main method. And we can see that we've created some points. So I have point P1. I'm using the constructor, the point constructor, to create 4 points, right, with various x, y coordinates. Great. And I'm using those 4 points in various combinations to create 2 triangles. And if I run this, oh, shit. OK, I have to go back and change all this, because there's too many references to change. So here's a little handy tip for you. If you want to rename a variable, you can just go to the variable's name and say, I think, Command Option R. And then it will put a little box around it, and it'll find all the places where you use that variable name. And now you can start typing, and it changes it everywhere until you press return, which is kind of cool. All right. OK. Now I should be able to run my program. Nope. What happened? This. Oh. Now this. Yeah, there you go. Funny. Now let's try it. Great. All right. So going back to my program, right, I have my points. I create 2 triangles. And the first thing I do is I print out the perimeter of those 2 triangles. And I see that the perimeter of T1 is 41 point something, and the perimeter of T2 is 63 point something. Fine, right? Now, you might imagine that, OK, how about if I wanted to take one of these triangles and move it over by 5 units in the positive x direction, right? You might think you could do something like the next 3 lines of code, right? So let's look at what these next 3 lines of code and how they work, right? I have a dot operator, right? And we know that a dot operator, the thing on the left of the dot operator is supposed to be an expression that turns into a reference of some sorts. And then, the thing on the right of the dot operator is either a field name or a method name that is being invoked, right, on that reference. So this first dot, the thing on the left, the expression on the left is T1. T1 is a name. It refers to this new triangle that was made out of points P1, P2, and P3. So that's my reference on the left of the dot, right? And so I'm referring to that particular triangle in memory. The thing on the right is A. That's a particular field in that object, right? And so for triangle, it's this point here. It's the A point of the T1 triangle, right? Which happens to be, this P1 point, right? So T1.A, that is going to resolve itself to be the A point of the T1 triangle. It happens to be the reference to P1, right? Because that was the reference, that was the point I provided the constructor to set the A point of the T1 triangle. So T1.A is going to be a reference to that point. We have another dot operator, right? So what's on the left? On the left is this expression T1.A, which we know resolves to this point 5, 5 that's somewhere in memory. And the thing on the right is a field name inside that point. So essentially, I'm taking the structure that was created here that happened to be, that P1 is pointing to, and that was given to T1. So T1.A points to that same point. And I'm going into that point, and I'm taking the x field, right, this double, and I am adding 5 to it. And that is perfectly OK for this code to do, because in that point class, that field does not have an access modifier. That means that field is available for access to any code in the same package. This Lecture 7 Example 1 program, that happens to be in the same package. And so the compiler does not complain, and this is perfectly fine. And so I've added 5 to the x coordinate of T1's A point, B point, and C point. And so if I just move T1 over, I would not expect T1's perimeter to change, and indeed, it doesn't change. But if I print out T2's perimeter, all of a sudden it has changed, which is a little odd, right? I mean, I define T2 here, I print out its perimeter, I only work with T1, and yet when I print out T2's perimeter again, now all of a sudden it's changed, right? So I'm going to give you a few seconds to confer with your neighbor and think about why that was, and then maybe we'll see if somebody volunteers a possible analysis as to why this happened, and we'll go from there. So discuss. Okay, let's bring it back in. Anybody have a theory as to why T2's perimeter changed when all I did was go through T1 and add 5 to each of its points as x coordinate?
Is it that when you change A for T1, it also changes the A of T2?
That's right. Well, it's actually not the A of T2. It's the, when I change the B of T1, I'm changing the A of T2. When I change the C of T1, I'm taking the B of T2, right? So, but exactly right. The idea here is that I've used the same points to define the two triangles. Not all the same, but some of the same, right? So the B and C points of triangle T1 happen to be the A and B points of triangle T2, right? Same reference, same object, right? So if I give P2 as a point of triangle T1, and then I give P2 as a point of triangle T2, yes, T1 does its job and stores away those references in its A, B, and C fields, but T2 does the same thing. And so I've reused 2 of the points, right? And so when I went through T1 and then went through its A, B, and C points in order to then modify the x coordinates of those points, I was also inadvertently, possibly, right, changing the x coordinate of 2, but not 3, of T2's points, right? And so T2, like basically what happened is, yes, I effectively moved all 3 points of T1 over to the right, and it didn't change T1's perimeter, but in doing so, because they have points in common, because 2 of those point structures are being used in T2, it also changed 2 of the points that were in T2, but not the 3rd. And that's why T2's perimeter changed, right? And that's the danger here of allowing code outside of the class to go in and muck with your internals, right? Because, maybe I don't realize that these points are being shared across triangles, right? And so when you develop a class, you want to adhere to this principle of encapsulation, which is you don't want to allow code outside of the class direct access to the fields. Instead, you want to mediate that access through methods so that you can control what gets to change and what doesn't, and how it can change, right? So that you can make sure that the object is always in a consistent state relative to how you intended it to be used. So what does that mean for us, right? In practice, right, the idea of encapsulation basically means you want to hide your state, right? You want to hide the fields so that they aren't accessible outside the class. So almost without exception, you almost always want to make your fields private. That way, by putting the private access modifier, it tells the compiler code that is not in this class, code that is not part of this class, should not have access to these fields, right? Well, okay, that's fine, but if I create a point with a private x and a private y, then how am I going to use that point, right? I mean, presumably I want to create points and then be able to work with them, and sometimes I might need to know what the x-coordinate of a point is. If it's private, how can I get to it? And so that's the other half of encapsulation, which is make your fields private, but then provide public, right, methods that can be used anywhere that can retrieve or alter those properties if you want them to be retrievable or alterable, right? And so the idea here is that if I provide a method that retrieves a field's value or a property's value, right, that is a getter. And if I provide a method that sets a property, that is a setter. The benefit here is that if I intend for a point to be immutable, in other words, I know that the points might be shared across triangles, so no one really should go in and change the x or y coordinate of a point after it's made, because you don't know who else is also using that point. So if my intention as an object designer is to create a point that once it's created always represents the same point and can never change, won't ever magically get its x or y value changed, the way I can achieve that is by providing a getter for the x value and a getter for the y value, but not providing a setter. And if I know that my fields are private and they're constructed at the time of object construction, and the only methods I provide are getters for getting those field values, and I never provide setters for those for setting those values, then I can reason about the object and say, I know that this object can never change, and then I can write in my documentation, this point is immutable, right? It can be shared across different structures like triangles without worry, right? So there's a certain convention for how we write getters and setters. And you'll notice on the last slide, I've started to use the word property rather than field. And I want to make a very clear distinction here. A field is a specific declared field in a class, instance field, in a class, which will have a value, is part of the object state, right? Properties of an object sometimes are directly reflected by fields, right? A point x value, right, is, there's a field x, which is its x coordinate, and then I might provide a getter for getting its x property, which happens to be directly reflected in the field, right? But we can also think of properties as, quantities associated with an object that I can get and maybe even set, but aren't necessarily directly tied to one specific field. So for example, area, we can consider a property of triangles, but there's no area field in our triangles. There's just 3 points, right? And so, I want to use the same conventions for talking about the area of a triangle as a property, right? So I want to provide a getter for the area property, but that doesn't necessarily mean there's an area field. Some properties are derived from the fields as a function of the fields, of some mathematical manipulation of the values of the fields, right? So this getter-setter convention applies to properties, which are quantities associated with an object, but may or may not have underlying fields that are storing that specific value. Okay? All right, so the Java Beans conventions for how to write getters and setters for properties of your object look like this. If you have some property P of type T, then the getter for that property should have the following declaration, right? Public, because this is something we're trying to expose. We want people to use the getter in order to get this value. T, which is the return type, right? It's going to return that type. Get as literally GET as the beginning word of the method, and then whatever the property name is as a using camel case, right? Basically, first letter of every word capitalized, right? And then it shouldn't take any parameters, right? If I do have a property that is allowed to be set, then the setter should have the following declaration if you're trying to abide by this convention, which is that we have public, again, because we're trying to expose this as something that can be set on our object. void, it doesn't return anything. The word set and then the property name. And then, of course, it needs to accept the new value of the correct type for setting that property. Now, I say these are Java Beans conventions. Java Beans is this a software engineering framework that used to be a lot more popular than it is now, but it's still pretty widely used. It's a whole set of associated tools that looks for methods in this form in order to understand what the properties of an object are, right? And so, so since it's still widely used, I still use it in this class, this convention, when I'm trying to define getters and setters for properties of objects, but it's a little old-fashioned. More modern stylistic conventions would not use get p and set p as the names of getters and setters. The idea of a getter and setter is independent from what you name it, right? The idea of a getter or setter is this idea of encapsulation. We'll hide the fields and make them private, and we'll mediate access to the fields either for retrieval or for setting them as properties of our object through methods that allow us to control whether or not they're settable or not, and whether or not, if they're settable, whether or not, to check the value to make sure that the value that we're trying to set it to, we have the ability to validate the value before we set it. Otherwise, if we don't do this, right? If we just make the field accessible from outside the class and rely on whoever's using the object to know, oh, you're never supposed to change that property, or oh, that value, that particular field is never supposed to be negative, or whatever, right? Then you're relying on the documentation and the other programmers' understanding of the documentation to not do some bad thing. This way, we prevent that programmer from doing some bad thing because they don't even have access to those fields. And if it's never supposed to be set, and I never provide a setter, then I know that it can't be set, and therefore, everything is safe. The other thing, the other part of encapsulation is to make a distinction between public behavior and methods that are only used, that are helper methods or internal methods that are part of my implementation, but are never intended to actually be used by code outside of the class, right? And so the idea here is that we separate a class into an interface and its implementation. Now, this is something new, something we haven't seen before, right? An interface in Java is like a contract. A class is an actual implementation. We're going to define what are the fields of this object, and we're going to actually provide the code for the instance methods that operate on those fields in order to implement those methods, that behavior for those objects, right? What an interface is like it's basically a contract of methods that a class can claim they implement. But the interface itself does not provide any information about how it's implemented. It basically just defines that a particular thing, a particular object can be called or implements this interface if it provides these methods, right? So it's just a list of public methods that are available. And you can write one or more classes that implement a specific interface. So that way you can have more than one way of implementing a particular interface. That interface name, right, it can be used as a type name, just like class names can be used as a type. As long as the object is an instance of a class that implements that interface, we can refer to that object via the type name that is the interface name. Right? So the way the actual syntax here is instead of classes, it's the interface keyword. So just like classes, interfaces go in their own .java file, and just like classes, they have the name of the interface should match the name of the file, but the body of an interface, unlike classes, does not contain any instance variables, right? Any instance fields, does not contain any code or constructors. All it does is it just has a list of method declarations that are the expected public methods of anything that is claiming to implement this interface. Right? You don't even have to use the access modifier public, because an interface, any methods listed in an interface, have to be public by definition. So if I have a public interface, some interface name, then inside the body of that interface is just a bunch of declarations, no code, right? So the return type, the method name, its parameters, and then instead of an open curly brace followed by code, we just have a semicolon. So it's just a listing of the declaration of the public methods that are expected by any class that claims to implement this interface. Once I have the interface defined, I can take a class which implements that interface, and I can make the connection between the class and the interface that it implements by declaring a list of interfaces that that particular class implements. So now we're going to add to our class declaration. So now instead of just public class name, we'll say public class, whatever the class name is, and then if it implements one or more interfaces, the keyword implements, and then a comma-separated list of whatever interfaces this class claims to implement. When I do this, right, that is essentially a declaration, that is a promise that in this class I will provide all the methods that have been declared by these interfaces as public instance methods available on any object that is an instance of this class. And if I do that, then when I have an object that is an instance of this class, I can use that object as an instance of any of these interfaces wherever I need a object that implements that interface. All right, so let's see what this. All right, so one more thing before we go to a specific example to see this in actual code. There are some naming conventions that often get used for interfaces and the classes that implement them. Again, you can name things whatever you want, but it helps to follow these conventions because these are widely used conventions, and so other programmers, when they see a name that matches these conventions, they'll understand it better if you use the same conventions. So one convention for interface names versus class names is to start all interface names with a capital I, kind of like Apple products, right? So iTriangle, iPoint, iPhone, I this, I that, right? And so the interface, like if you see a name, a type name or a name that starts with capital I, and you're using this convention, you understand, oh, they're referring to an interface name, right? And then the class names are essentially names that don't start with capital I, like this, right? That's OK. I personally prefer convention B, which is to use the generic abstraction name for the interface, and then any class that implements the interface, try to make a class name that is descriptive of how it implements that interface. So, and if there's no good natural way of doing this, just kind of use the same name but attach IMPL for, that stands for implementation at the end of it. So we'll see this in a second. Right. So let's apply these principles of encapsulation to our point class. So before we had something like this, where we didn't have any access modifiers, right? And we have a class point that isn't associated with any interfaces that says, okay, a point is going to be an x value and a y value. Here's how I construct it. Now, constructors should always be public, but that's OK. So here's how I construct it, and here is my instance method for calculating the distance from one point to the other, right? So the way we should do this is say, OK, if the idea that we're trying to capture is the idea of a point, then let's first define the interface point, right? So here's my interface point, right? So now I'm going to do it the way I'm supposed to do it, which is don't just create a class that is what you want and exposes its fields. Instead, define an interface that defines the behavior of the object, and then create a class that implements that behavior. And so now I'm defining an interface point. I haven't declared any fields. I don't know how this point is being implemented. I don't know whether its field name is X or Y or A or B or X chord or Y chord, and I don't need to know, right? Because a point that now a point is an interface that says any class that can provide a public getX method and a public getY method and a public distance2 method that takes in another point and provides a Boolean answer, and a equals method, I added another method, that takes in another point and gives me back true or false if these 2 points are the same point, right? That's a point. I haven't indicated how this is being done, but I just, I'm basically defining what a point should look like to the rest of the world, right? And so now that I have this interface point defined, now I can create a specific implementation of that. And so that is going to be my class Cartesian point, right? So point is my interface. Cartesian point is my class that implements point as a Cartesian point, right? And so Cartesian point, right now I'm using encapsulation. You'll see my fields, they're private. No one can get to them, right? Outside the class. And they happen to be called X and Y, right? My constructor for our Cartesian point has to match in the name, but that's the same. And now here are the public methods that are satisfying the contract that I said I was going to satisfy. Cartesian point implements point. That means Cartesian point promises to provide meaningful implementations of these methods. And so, right, it has a getX, which is a getter for its X value, and a getY, which is a getter for its Y value. And it has a distance2 method that takes in another point and is able to use getX, right, to get its own X, as well as getX to get the other point's X and to calculate a distance. And it also has this equals that says if 2 points are close enough. And again, I'm demonstrating how to compare 2 real numbers. I've defined a static point epsilon so that I have a named constant for deciding whether my x and the other x are close enough. And so I figure out whether the x is close enough, I figure out whether y is close enough, and I say, I return the and of those two. So as long as x and y are both close enough, then that's going to be true, and that's my implementation of equals. Now notice when I do this with oops. All right. So now when I do this with point, when I apply these principles of encapsulation to my point, how does my program change? How does my triangle change? Well, if you look at triangle, right? Triangle remains exactly the same. And the reason why is because triangle says you give me 3 things that are points. I don't care if they're Cartesian points or polka dot points or stripe points or or some other kind of point. I don't care. As long as it's a point, as long as it provides meaningful implementations for this interface, then triangle can say, you give me 3 things that implement point, and I'm fine, right? Because I will refer to those 3 objects. I don't actually know or care what real class they are. I just care that they're objects of they're instances of some class that implements that point interface. Now, triangle's view of that object is limited to just what that interface provides. So the class that is implementing point could also implement other interfaces and could also provide other public instance methods, but triangle asks for 3 points, and that's fine. And its view of those objects is limited to just that point interface, because that is what triangle is using. Right? And so, right, so in my right, so in my actual program where I'm creating points and creating triangles, when you create a point, you have to create a particular kind of point, but then I'm going to use it for the fact that it's a point. So this is the idea of programming to an interface. I want this object in order to represent a point, and therefore the type that I want to declare the name is it's a point, right? I want a reference to a point. But then when I actually create a new instance, I need to create, I can't say new point because interfaces are not implementations. So you can never say new and then interface name, because an interface name doesn't have the guts of a class, doesn't have the fields of the code to implement things. It's just a contract. When I use the new keyword, I have to use a class name, something that implements the interface that I'm trying to use. So I'm trying to create point P1, and I have to create some specific instance of a class that implements point. In this case, I'm creating a new Cartesian point to be my point P1. And now I have my point, I can use it with triangle, right? Now, we have not done, we have not separated triangle into an interface and a implementation, but that would be the next thing we want to do, right? So the advantage of this, right, is that we can create different implementations of the same interface. So here is my Cartesian point. So now I'm in version 3 of the Lex7.v3 package. Here's my Cartesian point that we saw before. I could also create a polar point, right? So if a Cartesian point stores an x and a y value, a polar point stores an r and a theta, right? And a polar point also implements point. So I have 2 classes. One that is a Cartesian point that implements point as an x and y value, and one that is a polar point that implements point as a theta and r. Now it changes what happens inside. In a Cartesian point, the x property, get x, is directly reflected by the x field that the Cartesian point is storing. In a polar point, I still have a getX property because I implement point, and point says that you must be able to meaningfully return a getX property, but my polar point has to do some math, right? In order to get x for my polar point, I have to combine r and theta using trig, right? And so here, this is, I still have a x property, I still have a get x getter, right? But I don't have an x field. Instead, my get x property for a polar point is derived from my field values by this mathematical function. Right? So, get x is r times cosine theta, and get y is r times sine theta, right? The cool thing is that, everything else remains the same, right? In order to calculate the distance to, it's the same distance to as the Cartesian point. I find my x, and and find the other guy's x. The idea here is this other point, I don't know what kind of other point it is. It could be a Cartesian point. It could be a polar point. But I don't need to know, because as long as it is a point, I know it will have a getX property, right? A getX getter. And therefore, I can use that method in order to retrieve a x value that is associated with that point. And I can use my own getX method in order to turn my, whatever I am into an x value and use that to calculate distance too, right? And then in a program, I could create 2 Cartesian points and a polar point those are all points, right? So I've just, P1 and P2 happen to be Cartesian points. P3 happens to be a polar point. But when I send them to triangle, triangle doesn't care because triangle is simply expecting 3 points. And those are 3 points. It just happens that this one is a Cartesian point, and this one is a Cartesian point, and this one is a polar point. But that's OK. Triangle doesn't really care what you really are. They just care that you satisfy this contract. And that's the big, that's kind of the big idea behind programming to an interface, right? So along those lines, we want to make a distinction between the behaviors that we want to expose to the rest of the world and any methods that we've defined as helper methods or auxiliary methods that really are just part of how we implement the things that we are exposing to the rest of the world, right? So the methods that we want to expose to the rest of the world, we really should define interfaces, one or more interfaces, that those methods are helping to implement, right? And mark them all public. And then all the methods that might just be part of, our internal programming for how we implement those interfaces, those methods that are not part of the interfaces that we're claiming, those we should mark private. Because if they were intended to be part of what the rest of the world saw, then they really should be part of one or more interfaces that we're implementing. All right. So the fourth version of this example essentially completes the exercise by applying these principles to both triangle and point completely, right? So now I have a triangle not as a class, but a triangle as an interface, right? So something that is a triangle must have a point getter, a get a method for getting its a point, and a set a method for setting its a point. So in this case, I envision a triangle that is not immutable, that has getters and setters for an a point, a b point, and a c point, right? It also has some other properties that that are derived from those 3 points. I can get all my points as an array of points, or I can set all my points as an array of points, and I can get my area and I can get my perimeter. Again, this is a contract for what an implementation of triangle should provide, but it is not an implementation in and of itself. And so then I take what used to be our triangle class, and I turn that into a point triangle. This is an implementation of triangle that happens to store the values it needs for implementing triangle as 3 points, right? That's why I call it point triangle. You can think of other versions of triangle that might do something different. You could have a point, a side length, and 2 angle triangle, right? I don't know what you would call that, but you could use different information to satisfy that triangle implementation, that triangle interface, and you would have a different class that used different kinds of information with different instance fields to satisfy that contract, right? So my point triangle takes in 3 points and stores them away, and then here are the kind of the public methods that implement the interface that I am promising to implement. So as a triangle, I need to provide a getter that retrieves my a point. So in this case, since the point triangle directly stores 3 points as its definition, this is a direct field. Like the property get a it happens to have a field inside this particular implementation, which is directly that property. So that's no big deal, right? Set a, well, so this now kind of shows us the power of encapsulation. If I want the a field of this point triangle to be settable, if I want to be able to change the points, instead of exposing the field and allowing it to be changed to anything, I would want to, I want to mediate that setting through a setter so that I can make sure that it's setting it correctly. In particular, I do not want to set my a point to any point that happens to be equal to my b or c points, because then I won't have a triangle, right? And, so I'm doing a little validation here to making sure that when when you set the A point, you're not collapsing your triangle. And then I set my A point to be the point that is provided, and then I do one last check. Right? It's like, oh, I want to make sure that the 3 points aren't collinear, because if they are, then that's not a triangle either. And so, here, this throw new runtime exception, this is how you basically bail out of a Java program, right? So when you discover an error and you just basically want to tell the user you screwed up, or the programmer you screwed up, there's something wrong, kill the program, you say throw new runtime exception and then whatever message. It'll kill the program and then and show that message as well as a stack trace, right? So using set A with a point that is illegal, right? Either the same point as B or C or collinear with B or C, that is, that my setter now checks for that and throws the appropriate error, right? And that's, again, the power of encapsulation. Hide the fields, mediate access through getters and setters, and have those setters validate the values. And then I have my get B, set B, get C, set C. Here's my get points where, oh, you want all the points as an array? Fine. I'll create an array with A, B, and C and give it back to you. Oh, you want to set the points? Well, then I'll make sure that all the points are not the same, and then I'll unpack them out of the array you gave me into my fields, and then I'll do one last collinear check. Right? Get perimeter, that was part of the interface for what a triangle had to do, and so I calculate my perimeter. You'll notice that all of these methods above this point here were part of implementing what was supposed to be the contract for what it means to be a triangle. I also happen to have a bunch of helper methods like checking collinearity and calculating the side lengths, right? There is no side AB length or side BC length or side CA length. That's not part of what it means to be a triangle. But it was convenient to have these methods as part of my implementation so that I could use them where I needed them in implementing my interface, right? But these methods are not technically part of my interface. And if they're not going to be part of the interface, then they're not for public consumption. They're only for internal use, and that's why they're all marked as private. Okay, this idea of defining and reasoning about a data type strictly through its behavior and not its specific implementation has a name, and it's called an abstract data type. In Java, interfaces is the mechanism by which we express abstract data types. And now we have officially bifurcated from 401, right? So when I did the same lecture in 401, I never mentioned abstract data type. Didn't even use the word, right? And now, but we are going to think about things a little bit more rigorously and formally about what it really means to model data and a data structure, right? So this idea of reasoning about a structure by its behavior without knowing anything about its implementation is this notion of an abstract data type. And that is what a Java interface is. It defines an abstract data type. Specific classes that implement an interface are known as concrete implementations of a particular abstract data type, right? And so, and concrete kind of gives you that sense of solid, right? Abstract, we just defined a whole bunch of behavior. We didn't define how it was going to work, so it's abstract. It's just an idea of a triangle, right? The idea of a point is that it has get x and get y. A specific kind of point, a concrete implementation, is a Cartesian point that does so with an x value and a y value, or a polar point that does so with an r value and a theta value. So interfaces, that's a way we model abstract data types. Classes, that's how we provide concrete implementations of one or more abstract data types. All right, which brings us to the very first abstract data type that we will work at as a data structure, and that is list, right? So this, you actually need to use lists in order in the next assignment. So if you haven't seen it before, if you haven't seen generics before, here's a little primer on generics. Java.util defines a interface, right? How do we know it's interface? Because it's an abstract data type. So, or how do we know it's an abstract data type? Because it's an interface. Either way. But list of E, and so this is the syntax for what's known as a generic interface. And you can also do it as a class, a generic class. It allows you to specify an interface or even a class, even an implementation, where it is related to some other type, but you don't know which type until you actually use it. In other words, I want to basically define what it means to be a list of a particular kind of thing, and I don't really care what kind of thing it is. I just know that when I use this list, I'll know what kind of thing I want to put in it. But when I, when I want to code the interface, when I want to code a class that implements this list, I don't know what kind it's going to be. So what I do is I put this angle bracket, and then I put in a placeholder. And then I can use that placeholder, and it's usually a one-letter placeholder, usually a capital letter. I can use that placeholder in my interface definition or in my class implementation, wherever I need to refer to the type that this is eventually going to be. So I know that when I use it, I will provide a specific type name in those brackets. But when I'm coding it, I don't know what that type is in advance. And so I need something as a placeholder for wherever that type is going to be, right? And so this is an example of what's known as a generic. So, list of E, that's how it's defined in the library. But when I use it, I have to provide a specific type name for that E. So I can have a list of strings. I can have a list of triangles. I can have a list of points. I can have a list of string arrays, right? Whatever it is that you want in this list, right, you have to provide that type at the time that you use it. Now, the only restriction is that E needs to be a reference type. It cannot be a value type. It can't be list of int or list of Boolean with a small b, right? But there's a way around that I'll show you in a second because you'll need to use that for the assignment. What is the list abstract data type? What is its behavior? How is it defined? If you go to the documentation for list in Java, basically list allows you to create a list that can grow. So unlike arrays, which is basically a set piece of memory that has a certain number of elements and you have to know exactly what size it is when you make it, a list is a structure, it's an abstract data type that can grow, right? So you can add things to it, you can take things out of it, and its size gets bigger or smaller, right? And so a list, right, has these behaviors that define it as an abstract data type. You can add an element to a list. You can add an element to a specific spot in the list, and moving everything else down. You can get a specific index from the list. So like arrays, a list has a certain size and is indexed by 0. You can remove a particular index from the list, and then you'll get back the element that you just removed. You can remove the first instance of a particular element in the list, and you'll get back true or false if it got removed. And you can ask the list what size it is. You can do other things with a list, but this is kind of the minimum things you need in order to have a list, right? Now, list of E, that's the interface, that's the ADT. In java.util, in that package, there are two implementations of this list, array list and linked list. And when you're using a list, you don't really necessarily care what kind of list you have because you're programming to the ADT. You're saying, oh, give me a new array list because I need a list, but then the thing you're using is a list. And you don't really care if it's an array list or a linked list or some other kind of list. You just need it to support these operations as a list. Right. I'm not going to go through the example. I'm going to let you go through that on your own. It's a little scanner loop that exercises these methods on a list. I just want to make one last comment here. Is I mentioned that you couldn't use these generics with with primitive value types. In order to get around this, Java provides for every value type, there is a corresponding object that represents that primitive value. Okay? So for the ints, there is integer with a capital I. For the character, for car, there's character with a capital C. For Boolean with a small b, there's Boolean with a capital B. The capital versions, right, are object versions of the primitive data types, and you can use those type names with generics whenever you're trying to use a generic with a primitive value type. And what Java does is it'll automatically convert values to their corresponding objects and vice versa, and that's called boxing and unboxing. It does that for you. So if you want a list of ints, you can't say list of int, you have to say list of capital I integer. But that's okay. Wherever you need to provide a value to add something, you can provide an int, and then when you retrieve something out of the list, it'll automatically turn back into a primitive value type. All right, so we'll pick it up there on Tuesday. There's going to be a reading assignment for Tuesday that I'm going to post on Sakai, so look out for that. It'll come out tonight. And then on Tuesday, we'll dive into list, its implementation as array list and linked lists, and then specializations of lists.